So now what we're going to see is section 5.2. And as you can see here, we're going to see what trig functions are. We're going to see the definition of the trigonometric functions. And again, as I said before, we're only going to focus on angles that are in a right triangle. In other words, we're only going to focus on angles that are between 0 and 90 degrees. Those angles are called acute. We're also going to see how to calculate the trig functions of certain explicit angles. In other words, we'll see later how we actually get a sine of 45 degrees. We'll see also what sine of 30 degrees is. What's nice is you don't have to memorize those values. They're programmed in your calculator. Pretty confident, let me just check. Pretty confident the iPhone calculator has that, and looks like it does. Yeah, you just want to make sure you're in the right mode though, because if you're in radians, you want to make sure you're in the right mode. You want to make sure you're in. If the calculator's in degree mode, you want to know that and make sure you're working in degrees. But if you want to work in radians, make sure your calculator is in radians. If you want to work in degrees, make sure your calculator is in degree mode. All right. Well, let's get to this. Well, to actually define the trig function, we need this setup. So we have a right triangle. A right triangle, again, is a triangle where one of the angles is 90 degrees. That's just a definition. This little this little square down here denotes the 90-degree angle. You can kind of see it from the way these two lines are situated. These two sides, that is. But this just tells you, this confirms this little square, the angle is 90 degrees. As I said before, we generally like to use Greek letters to denote angles. So I'm using theta here, Theta, theta. I know some places, some other notation might be alpha, ALPHA, Greek letters like that. I think it's just convention. So then what we do is this. We're going to label these two sides relative to their position with theta. This side here, OPP, stands for, that side is called the opposite side. OPP stands for the length of this side. This is the side opposite theta. So OPP is the length of the side opposite theta. This ADJ, this is the side next to theta. It's the length of the side adjacent to theta. Hype, HYP, that's the length of the side opposite the 90-degree angle. No matter what theta is, hype is always opposite the 90-degree angle. It's called the hypotenuse. And hype stands for the length of this side, the side opposite the 90-degree angle. Note also, it's actually the longest of the three sides. It's the longest of the three sides. You could actually take this angle to be your theta if you want. This would not change, but these two would interchange. They would interchange position. And what I did is fine now. Let me just say this also. If you have two of the angles in a triangle, you know the third angle, right? Because the sum of the angles has to be 180 degrees. Okay. All right. now let's actually get to the definitions of these trig functions. So again, it's defined using the length of these sides. So sine of the angle theta is equal to the opposite divided by hypotenuse. It's equal to this fraction. Again, this is just a definition. Cosine of theta, this is sine of theta. Cosine of theta, that by definition is the adjacent side, the length of it, divided by the length of the hypotenuse side. That's what this is telling us. Tangent of theta, by definition, is the length of the opposite side over the length of the adjacent side. Again, this is all definition. I think the Greeks were the one that came up with this. Pretty sure they were. Now, this is a lot to remember. I understand. That's why we have this SOHCAHTOA. It's a way to remember it. So S here is sine. O is opposite. H is hypotenuse. C is cosine. A is adjacent side. And T is tangent. It's just a way to remember these three. That's all. Let me say this also. Hypotenuse is the longest of the three sides. So OPP, opposite side, that's smaller than hypotenuse. That tells us sine is positive and less than 1. Less than or equal to 1, I should say. So if you're doing this and you get sine of theta to be a number like 2, then you did something wrong. Same thing with cosine. Sine and cosine, they're both greater than or equal to 0 and less than or equal to 1. Well, actually, they both have to be positive. So tangent could be bigger than 1 because you can have the opposite side greater than the adjacent side. That was just something I wanted to point out. Okay. We also have these three definitions. These three, I'm not sure if there's a device like SOHCAHTOA to remember these three. Secant of theta, cosecant of theta, cotangent of theta. We have these three as well. What does turn out to happen, though, is there are identities we can use to remember these three. And that's what this is. It turns out that these aren't the definitions of secant, cosecant, and cotangent, right? These are. So they are defined, like secant is, as you can see, hypotenuse over adjacent. Cosecant is opposite over adjacent, hypotenuse over opposite, and so on. We do have these identities called reciprocal identities. These you can use to remember the trig functions. I mean, I do. That's how I remember it. I can't remember the definition. I can't remember these three definitions. I just can't. So I just use this. It actually just follows easily from the definitions, though. So cosecant is 1 over sine of theta. Secant's 1 over cosine of theta. Cotangent is 1 over tangent of theta. In fact, you can actually get tangent and cotangent, as you can see here, in terms of sine and cosine. Again, it's just all from the definition. There might be a little bit of algebra there. I know for tangent there is. But it turns out this is true. Okay. So let me see. So also the definitions that we saw, not just these identities, but the definitions on the previous slide, they hold regardless if theta is in degrees or in radians. It doesn't matter. So whether theta is in degrees or radians, it doesn't make a difference. Now, I threw this in here also. I figured it would help with the algebra. But generally, if you have 1 over something, like a fraction, you end up flipping the fraction. You invert it, that is. So 1 over a over b, right? That's going to be b over a. 1 over a over b, that's going to be b over a. Again, that's just the definition. No, not definition. What am I saying? That's just algebra. I'm sorry. So 1 over a over b is b over a. Again, this is just saying that if you have 1 over a fraction, you invert the fraction. The numerator becomes the denominator. The denominator becomes the numerator. This will actually help when we're dealing with these. And really for these as well, we have this. You can really use both, I guess, but if you have a over c over b over c, it's really not hard to prove algebraically, or you can just use the definition of dividing fraction. That this turns out to be the same as a over b. So these denominators in this big fraction, these denominators here go away. That's what happens. This is what happens. And again, also I'm assuming a, b, and c are not 0 because you never want to divide by 0. So. And also we have this famous theorem called Pythagorean's theorem. You have this theorem, Pythagorean's theorem. And this is really nice because this is telling, well, let me say the theorem. So C is the length of the hypotenuse. A and B are the lengths of the two legs. And A squared plus B squared is C squared. Yeah, that's very nice because if you know 2 of the side lengths of a right triangle, you can easily get the third using this. But triangles in general, that's not the case. That's what's really cool about this. Pythagorean's theorem. Let me just stop the recording.